So this next little section that we're going to do is something called resonance structures. And what resonance structures are basically when a compound cannot be drawn with just one Lewis structure. So when we can't depict it with just one structure, it doesn't show us an adequate picture. So a resonance structure is a two-dimensional representation of a compound that can't adequately be.
Like 2D?
Yep. Okay, so this is kind of my definition. The book, I'm sure, has something different. A 2D representation of a compound that can't adequately be shown with one Lewis structure. Okay, so that, I think, is probably a little foggy for you right now. So what happens if we have Lewis structures that are not symmetrical or are not, not even on both sides? So far we've dealt with ones that, are very symmetrical or in terms of like, if we have a double bond on one side, we usually have had a double bond on the other. Okay, so the way that resonance structures work is it allows us to show basically a movement of electrons if needed to help kind of balance our molecule. And resonance structures can get much more complicated than what we're really going to kind of make them or dive into. But we are going to look at a few examples of what it means to have a resonance structure. Okay, so a resonance structure is basically just more than one Lewis structure. So let's just try a couple examples here. We're going to look at first carbonate, which is CO3 minus 2. Okay, so carbonate would have 4 plus 18 plus 2. Right? You know where that 2 is coming from? The charge, that's right. So that gives me, I think, a total of 24 electrons. Would you agree with that? Okay. So my skeleton should look something like this. C-O-O-O. Okay. So now I'm going to put in my bonds. That means I've used 6. And I have 18 left. Okay, so what seems to be the obvious choice here? Fill in our oxygens, right? 2, 4, 6, 8, 10, 12, 14, 16, 18. Right? That seems like it's working fine, but what's the problem?
We have none left and carbon isn't done.
Perfect. We have no extra electrons, and carbon does not have a fulfilled octet. And carbon is not cool with having an incomplete octet. Okay? So we've used all of our 18. What have we done in the past to help us fulfill an octet if we've maxed out our electrons? We've bumped a lone pair into a double bond. But here's the problem. How do we choose which oxygen to do that from? Because we are only going to need one of those double bonds.
Does it matter?
It doesn't. But we have to show the structure with all 3 possibilities. Okay? Because essentially what's happening here is that this, let's say we bump this lone pair into a bond. What's happening is that those electrons kind of realistically float between all 3 bonds. Okay, and that's more than we really need to know at this point. But what we do is if we pick this oxygen, we'll double bond here. Okay, so now we have a completed Lewis structure. But it doesn't give us a correct representation of the molecule because this is not the only oxygen that could occupy that double bond. So what we do is we draw the exact same thing, except now our double bond goes to a different oxygen.
So are we just drawing all possible possibilities.
Yeah, you have to draw all the possibilities. That's what makes it a resonance structure, is that you have more than one representation for that compound. Okay, so do we need one more?
Yes.
Yes, because it has to double bond to that last oxygen. Oh, sorry. Oops. I did something silly. On that double bond, we only get 2 lone pairs.
I was about to say.
Oh, were you?
But I don't know. She's a teacher, so I wasn't trying to correct her.
Well, sometimes, I make mistakes. Okay, so this shows all versions of carbonate now. There's 2 things that we're missing with resonance structures that we have to include. The first of which is a double-headed arrow in between structures. And what these arrows tell us is that these structures represent the same molecule. Okay, they represent the exact same molecule. They're just different versions. Okay, the last thing that we need with a resonance structure, we only need when it has a charge. But we put brackets around the whole thing, and we put the charge on the outside.
Oh my gosh.
Okay, so that right there is a finished and complete resonance structure for carbonate. Can you what?
We never do this.
I know. I will always tell you if one needs a resonance structure. Okay, so I'll give you the clue if you need to draw a resonance structure. Resonance structures are always about floating that double bond. Okay, so if it says to draw a resonance structure and you don't have a double bond, right, that's a problem because that's what it is, right? It's about moving that double bond around. And it gets more intense than that, but that's what we need to know about it. Okay, so you have to move that double bond between those 3 oxygens. Okay, sometimes you can have only 2 resonance structures, sometimes you can have 4 or whatever. Okay, but that's what we need to have. We got to have the arrow and we got to have the charge with the brackets. If you don't have a charge, you don't have to include the brackets. Okay, if there's no charge, you don't have to include the brackets. Okay, let's try this one on your own. C2O4 minus 2.
Is it okay, to do, one, it going, long ways? So, put the brackets, soup, and the resonance in the middle, or no?
You mean put one right on top of the other?
Yes.
Yeah, that's fine.
Okay, that's fine. There's a lot of different.
There's a lot of possibilities. Maybe not quite as many as you think, but yes, there is a lot. Should be 4. So on this one, I want you to really think about the fact that we could not have had double bonds here and here, right? That would have caused an overload on carbon. So when we're looking at moving that double bond around, right, we can go on the diagonal, and then we can go both on top and both on bottom, but we can't have, both of our double bonds happening on the same side, okay? Yeah, McKenna.
Why don't you have 8 on oxygen?
Sorry, I just didn't fill in the electrons.
Oh.
So the lone pairs, I left all of those off.
Okay.
So you still do need lone pairs on all of those oxygens, that's right. I just left those off because I didn't want to draw them. But when you're drawing those lone pairs, it is important that the double bonded oxygen only gets 2 lone pairs, right? The single bonded oxygen does need to have 3 lone pairs. Okay, are we on the same page with that? Okay, I chose to just leave off my electrons for time purposes, but you would need to have all those. And then we'd have our double-headed arrows. And we include our brackets. Okay? That's a lot. I won't ever give you usually more than 2 or 3 resonance. Okay? So having 4 is a lot to ask. And this one is a little more complex than ones we'll get into. So if we have resonance structures in the future, I will specifically ask you, include all resonance structures if you need one. Okay? If I don't say that, then means we probably don't need a resonance structure. Okay?